Welcome to This Explainer. I'm so thrilled you're here. We are jumping right into a seriously fascinating physical phenomenon that secretly runs so much of the world around us. We're talking about the mechanics, the math, and the real-world applications of pressure in solids. I mean, if you've ever stepped on a stray Lego in the dark and wondered why such a tiny piece of plastic causes an astronomical amount of pain, or on the flip side, why massive, heavy tractors don't just sink straight into the mud, well, you're in the exact right place. We're going to decode the invisible rules of force and area together.
Here's our quick roadmap for today. 1. Defining pressure. 2. The two rules. 3. Real-world applications. 4. The glass block puzzle. And 5. Exam tips and review. Let's get to it.
Step right into our 3D physics laboratory. We've got our weights, sandboxes, chalkboards, the whole shebang. We're going to use this virtual lab space to transition away from those boring abstract definitions and really visualize how force and area interact. Because, understanding physics isn't just about memorizing some random equations. It's about seeing those equations come to life in the physical space right in front of you.
Section 1. Defining pressure. So what exactly is it, and how is it different from just a simple push?
Imagine pushing against a foam wall with a flat hand. The force is spread all out, right? And the foam barely yields. But what if you take the exact same amount of force and apply it using just a single pointed finger? It digs deep into the foam. I want you to hypothesize for a second. Why does the exact same amount of effort create such a drastically different result? Well, the secret, as you might be guessing, lies entirely in how that force is distributed. And that awesome visual observation leads us directly to the math. Pressure equals force divided by area, or simply, P equals F over A. We measure force in newtons. You can just think of the weight of an apple for that one, and we measure the contact area in square meters. When you divide the force by the area it's spread across, you get your pressure, which is measured in pascals. Honestly, it's a beautifully simple ratio that explains just so much of our physical reality.
Moving into Section 2. The two rules. Let's uncover the mechanical rules that dictate how pressure behaves. This brings us to a crucial point, our first rule, which I honestly like to call our golden rule. Area matters. Imagine two 50-Newton weights. They weigh exactly the same, but one of them has been modified to rest on a tiny, sharp point. Because that contact area has shrunk so drastically, the force becomes hyper-concentrated. The pressure absolutely skyrockets, literally shattering the tiles beneath it. The big takeaway? If you keep the force constant but shrink the area, pressure always goes up. Rule 2 is just as intuitive. Force matters. Picture two identical blocks resting on some soft clay. The first one has a 10-Newton weight on it, creating a nice low pressure that barely even dents the clay. But for the second one, let's stack 50 newtons of total weight onto that exact same surface area. Because the area is totally identical, but the downward force has seriously increased, the pressure jumps way up, driving the block super deep into the surface. Let's quickly cement this math in our mental lab notebook right now, because getting this relationship is absolutely key to everything else we're discussing today. Ready? Force is directly proportional to pressure. More force means more pressure. Simple enough. But area? Area is inversely proportional. More area actually means less pressure. So if you want to drop the pressure, you spread things out. If you want to spike the pressure, you focus it down. Let's see this golden rule in action at the lab stations. In our sand test, a smaller block sinks so much deeper because its smaller area concentrates the weight, creating way higher pressure. Or think about a sharp pin easily piercing a tough piece of cork, compared to a blunt metal spatula that just leaves a shallow little mark. That pin's tiny area generates a massive amount of pressure with almost zero effort. It's really cool to see. Section 3. Real-world applications. Let's see how engineers manipulate these exact variables out in the wild.
Let's actually apply what we've just learned. Sometimes we intentionally design for high pressure. Think about a stiletto heel. It concentrates a person's entire body weight into a tiny, tiny dot, which is exactly why it can easily damage a soft wooden floor. Or a chef's knife. It's sharpened to a microscopic edge so it can slice right through an apple with barely a tap. But on the flip side, we often design for low pressure. A massive, incredibly heavy tractor doesn't sink into a muddy field simply because its enormous, wide tracks spread that huge weight over a massive area. The exact same biology applies to the wide, flat feet of a camel walking on loose desert sand. So, to totally summarize this engineering mindset, if your goal is to pierce or cut, your design choice must be to decrease the area. You utilize tools like knives, pins, and stilettos. But conversely, if your goal is to float, protect, or prevent sinking, your design choice has to be to increase the area.
using wide tractor treads, snowshoes, or, relying on nature's design like those camel hooves.
Section 4. The glass block puzzle. Let's test our problem-solving skills with a classic physics scenario.
I want to challenge you right now to put on your physics detective hat. Imagine a single solid object with a fixed weight. Can that single object exert entirely different pressures on a table without changing its weight at all? And if so, how do we maximize that pressure?
Picture a standard rectangular glass block. It has 3 distinct pairs of faces. Face A is the largest, it's wide and flat. Face B is the medium-sized side. And face C, right on the end, is the absolute smallest area. Consider the geometry we're dealing with here. Which of these faces, when you place it flat on the table, will concentrate the downward force of the block's weight the most?
Now, to solve this puzzle correctly, we can't just guess, right? We have to methodically follow 3 steps to turn our visual hypothesis into cold, hard data. First, we identify the force. Second, we identify the specific contact area for whatever orientation we choose. And third, we calculate it by applying our trusty formula, P equals F divided by A.
Let's run the numbers. If our block exerts 60 newtons of force, and we stand it up on a face with a tiny contact area of 0.20 square meters, well, boom. 60 divided by 0.20 gives us a precise pressure of exactly 300 pascals. It really is that straightforward once you identify your variables.
And just like that, the puzzle is definitively solved. Standing the block vertically on its smallest face, face C, is absolutely the correct answer. The weight of the block, which is our force, is the exact same no matter how you turn it, but resting it on the smallest possible area concentrates that force to its absolute limit, creating the maximum possible pressure exactly according to our golden rule. You totally cracked the case.
Section 5, Exam Tips and Review. Let's wrap this up with a handy cheat sheet.
When you map it all out, everything we've covered today just connects so beautifully. It's like a giant puzzle coming together. From that central core formula of P equals F over A, to the mechanics of area decreasing while pressure increases, all the way to practical, everyday results like the high-pressure danger of a stiletto heel versus the low-pressure safety of a snowshoe. It's a complete, totally interconnected system.
Before we go, I want to leave you with 3 vital takeaways. Number 1, always write the formula down first to ground your thinking. Number 2, double-check your units. Force must be in newtons, area in square meters, and pressure in pascals. Number 3, always remember the golden rule. Shrinking the area inflates the pressure. Keep these in mind, and you are golden. As we sign off, I'll leave you with this final provocative thought. Now that you understand the math behind force and area, what other invisible physical forces in the world around you can you suddenly start manipulating to your advantage? Thank you so much for joining me on this explainer, and keep exploring.